However, we still do have mirror planes in this molecule. If we look along this particular line here, we can see printed on the model, we have a sigma V for a vertical mirror, and we can see, if we turn around this direction, that if we open along here, that the one side is the mirror image of the other. The central atom is cut in half, the axial ligands are cut in half, and we have mirror images along the equator. So we see that this particular molecule does have 3 different vertical mirrors. Essentially they're all identical to each other, just going through different of the 3 equatorial atoms. So here we can see, even though we don't have a horizontal mirror, we still have 3 vertical mirrors. This tells us that the point group assignment for this particular substituted molecule is C3V. So C3 is one of the possible subgroups that we can get when we start to substitute the trigonal bipyramid. Now let's see what we get when we substitute both of the axial positions to the same type. Here they're denoted as yellow. So even though the 2 axial positions are different types of atoms than the 3 equatorial positions, the 2 axial positions are the same ligand. So again, we want to see what is the high order rotation axis for this particular molecule. So we'll turn this way, and again we can take a look and see what happens when we do a C3 rotation. So if we turn counterclockwise by 1/3 of a turn, we see that all the atoms line up. If we go clockwise by 1/3 of a turn, they also line up again, which tells us that C3 to the -1 is a symmetry operation of the group. C3 is the high order rotation axis. Again, if we look along the equatorial positions, we do have a C2. We rotate by 180 degrees. We'll see that we transform it exactly to the same position that it was before. So this particular molecule has 3 C2s that are perpendicular to the C3 axis, the high order rotation axis, which tells us that we have some type of a D3 group. The only question remaining is about the mirrors. So let's take a look and see what type of mirrors are available in this particular molecule. One of the mirror planes is along the equatorial position, which we can see denoted in this particular model this way. And because this particular mirror plane is perpendicular, it's normal to the high order rotation axis, this makes it a horizontal mirror. And in fact, the model will tell you, hi, this is a horizontal mirror plane. Yes. Anyway, so because it has a horizontal mirror plane, it has a C3 high order rotation axis, and it has 3 C2s that are perpendicular to the high order rotation axis. That tells us that we have the group D3H. So we see by substituting at the axial positions where both of the atoms are identical, we are back to the point group D3H. What about vertical mirrors? It turns out that this molecule also has vertical mirrors. We can see it printed along the model here. We have a sigma V, which shows where the mirror plane goes, and we can animate our model to see what it looks like by opening along here, and we can see that along the mirror plane, the left side and the right side are mirror images of each other. They slice directly through the central atom and through the 2 axial positions and through one of the 3 equatorial positions. So because there are 3 different identical equatorial positions, we have 3 vertical mirrors, 3 sigma V's. And we can denote them and animate them using this type of a molecule. So we see that in point group D3H for the trigonal bipyramid, not only do we have 1 horizontal mirror, but we have 3 vertical mirrors also. Here we have one more example of a substituted trigonal bipyramidal molecule. So in this case, the two axial positions are identical. They're both blue. We have one red but two yellow equatorial positions. So because we have different equatorial positions, if we look down the high order rotation axis, this model isn't built to rotate, but if we did do a rotation, what you would see is that we no longer have a C3 rotation axis for this particular molecule. So the C3 axis has been removed by the way we have substituted at the equatorial positions. We would still like to know what is the high order rotation axis. And it turns out for this particular type of molecule, if we look along this particular, an axis going to this position, that if we rotate by 180 degrees, we would get the exact same position that we had before. So going through the equatorial positions, we have a C2 rotation axis. So for this particular substituted molecule, the high order rotation axis is a C2. It also has a couple of different mirrors. One of the mirrors we can see, display it this way, can open up along the equatorial position. We have a mirror. Now, one thing to keep in mind is because the high order rotation axis is not going through the axial positions, this is not a horizontal mirror. This is just a vertical mirror. And it turns out that it includes the C2 axis. So it's another evidence for us that it is not a horizontal mirror. It is just a vertical mirror. And we can see that we can animate, and we see that the vertical mirror, that the top and bottom positions are really mirror versions of each other. So that truly is a mirror. There is also another mirror plane that goes along this direction here. So it basically goes through the axial position and through the central atom, which is another vertical mirror. Because we have a C2 high order rotation axis, we have two vertical mirrors, and of course we have the identity operation. This reduces the symmetry of this particular substituted trigonal bipyramid to C2V.